Hello everyone, welcome to my video on integration by parts for definite integrals. So we saw integration by parts for indefinite integrals. We went over our strategy, LIATE, where we identify how to choose our u. But here we're going to look at the same notion just for definite integrals. So basically if we have f prime and g prime, which are continuous functions, we have the integral from a to b of f of x times g prime of x dx, and that's equal to f of x times g of x evaluated from a to b minus the integral from a to b of g of x times f prime of x dx. This is essentially the exact same formula that we saw in the previous video for indefinite integrals, but now for definite integrals we just define our bounds. So basically it's the same notion that applies, and again this is difficult to memorize, so an easier notation to use is the integral from a to b of u dv is equal to u times v evaluated from a to b minus the integral of a to b of v du. Okay, so this we saw, and just remember our LIATE strategy. If you want, you can go back on the previous video to look at the strategy, but just quickly, how to choose the u? Well, it's based off log functions, inverse trig, just gonna go over it quickly, algebraic functions, basically polynomials, t is for trig functions, and e is exponential. Again, this does not work 100% of the time, but this is the order in which we decide what to call u. Logs being the first, inverse trig being the second, algebraic functions being the third, trig functions being the fourth, and lastly our exponential functions. Okay, so keeping LIATE in mind, so this is the acronym we're using to call our u. Let's go ahead and solve our problems. Okay, so in our first example over here, it says to evaluate the integral from 0 to 1 of x divided by e to the 2x dx. Okay, so remember integration by parts, we're using it when we have essentially a multiplication of two different types of functions, but here we don't have a multiplication, we have a division. How do we deal with this? Well, one thing we could do is just rewrite the e to the 2x as the integral from 0 to 1 of x times e to the negative 2x. Okay, and now we could see we're dealing with a algebraic function and an exponential function. So let's go ahead and apply our LIATE trick. So algebra, exponential. Looking at LIATE, we have a and e. A, the algebraic function, or the polynomial function, is just x, and the exponential function is e to the negative 2x. So what do we call u? We let u equal x. Okay, so let's go ahead and solve that. So u is equal to x. That leaves us with dv. So this is our setup. We want to go get u du. We want to get dv and v. Okay. So if this piece is our u, whatever's left over is the dv. So in this case, it's e to the negative 2x dx. And from u to get your du, you have to take the derivative. And from dv to get to v, we have to integrate. So let's go ahead and do that. So deriving x, let's just write it here. We're deriving with respect to x. We're taking the derivative, d dx. The derivative of x with respect to x is just 1 dx. Here we're integrating. Okay, so this you might have to do on the side. How do we integrate e to the negative 2x dx? Okay, so here let's put an integration symbol. Well, let's do it on the side just in case you're not able to do this in one shot. What we're really doing is a u substitution. So we're integrating, this is side work, e to the negative 2x dx. Okay. Really what you're doing is using a u sub. So we're letting u equal, let's call it u bar, just not to use the same u as here. So we're letting u bar equal negative 2x, whatever's in the exponent of the e. And the derivative of u bar with respect to x is negative 2 dx. Solving for dx, we could divide both sides by negative 2, giving us e to the u, and dx is equal to du bar over, sorry, I should call it du tilde, and dx is equal to du tilde divided by a negative 2. Okay. Taking out the negative 2, or the 1 over negative 2, negative a half, we're left with e to the u bar, du bar, or du tilde. And this is just essentially the integral of e to the x, which we know is e to the x. So this gives us e to the u tilde over negative a half. Oh, sorry, times negative a half, because we have our constant in the front. Okay. And going back to what x is, u tilde is equal to negative 2x. So this is simply just negative e to the negative 2x over 2. And that's our v, e to the negative 2x over negative 2. Okay. You might have been able to do this just simply without doing the u substitution, knowing that essentially what you're doing is you're taking the constant that's in the exponent, the negative 2, and dividing by it. Okay, that's the shortcut. You can see these tricks later once you get more experience with u substitution. But at the beginning, especially, what you should do is actually go on the side and solve this by a u substitution. Okay, actually do the work. Once you're comfortable, then you could start taking shortcuts. But at this point, do the work, do the side work, and we get the integral here. And now we apply the integration by parts. So the formula that we're using, keeping in mind, it's the integral of u dv is equal to u times v minus integral of v du. But now it's defined from a to b. So it's definite integrals, a to b, and a to b. So this is the formula we're keeping in mind. Again, we follow the process from top left multiplied by the bottom right, and then minus the integral of the bottom right times the bottom left. So this is, again, side work. And now we're jumping from this piece over here all the way down to here. So we're going to change its form. So we get u times v, which in this case is x times e to the negative 2x over negative 2. And we're defining this from a to b. And in our case, our lower bound is 0, our upper bound is 1. Notice that we do not change the bounds of integration. For a u substitution, the bounds of integration change. For integration by parts, you don't. You leave them the same. Okay, so it's 0 to 1 minus the integral from 0 to 1 of v du. So now you're multiplying this piece here, the e to negative 2x, over negative 2, times this piece here, which is just dx. Okay, and now this is what we have to deal with. This part here, we could apply FTC part 2. We could evaluate out the upper bound, subtract by the lower bound. And this piece here, we have to integrate it again. Okay, so let's go ahead and do that. I'm just going to give myself some room and erase the top. This one over here, you should know the integral right away based off the first pattern that we saw. We took what's in the exponent, the constant, and divided by it. When you're integrating this again, you're essentially doing the same idea. You're taking the integral, the constant that's in the exponent, and you're going to divide by it. So I'm expecting here to get a positive 4 on the bottom. But let's go ahead and use a u substitution and show our work. We won't skip steps. So this piece here on the side, the integral, I'm going to take out the 2 negatives. So here we have 2 negatives, so that becomes a positive. Just easier to work with, and we're going to deal with this. So the integral of a half, I'm pulling this piece out, the constant out, and we have the integral from 0 to 1 of e to the negative 2x dx. And again, we're going to apply a u substitution. We used u tilde, let's use u bar now, just not to get confused with the notation. U bar is equal to negative 2x. The derivative of u bar is equal to negative 2 dx. Solving for dx, we could do that. This is a u substitution. So now we do have to change the bar because I'm applying a u sub. So the lower bound becomes 0 because 0 times negative 2 is 0. And the upper bound we have to switch. It's 1. We're replacing the x with 1. Negative 2 times 1 is negative 2. Okay. So now we're in terms of u. We get e to the u. And the dx, you could solve for it by dividing both sides by negative 2 here. So we get du bar over negative 2 equals dx. Oh, sorry, this is u bar. And dx is being replaced with du bar over negative 2. Not negative 4, negative 2. And as expected, we essentially just divided by the constant that was in the exponent. And I'm going to pull this out, giving us a negative 1/4. Integral from 0 to negative 2 of e u bar du bar. Okay. So that's this piece over here. So let's go ahead and give myself some room and solve this. This one here, we can evaluate it right away might as well do it here. I'm gonna put the integral of e to the u or e to the x is e to the x. It stays the same, so we have e to the u bar. Because it's a definite integral, I don't have to go back in terms of x. If it was indefinite, then I would have to substitute back my original x. But in this case here, you could just apply FDC part 2 right away. Okay, so we have the upper bound, which is -2, and the lower bound, which is 0. Okay, so that's this piece here. This piece here is this over here. So let's erase and make some room. So here we have x times e to the -2x over -2 from 0 to 1. Plus this piece, which we just solved for, is here. Plus, well, it's -1/4, open bracket, -2 to 0. So e to the e to the u bar from 0 to -2. Okay, let me erase all this. Okay. So this is going back to our original integral, and we just have to apply FDC part 2 at this moment here. So evaluating the upper bound, we plug in 1 here. So we have 1 times e to the -2 times 1 over -2 minus, and now you plug in 0, but since there's an x, you're multiplying the whole thing by 0, so this is just -0. This is FDC part 2. We just substitute the upper bound 1 and subtract by the lower bound 0, giving us this, and then we have -1/4. And same thing here, you substitute the upper bound, so e to the -2 minus e to the 0. Okay. Again, I have to erase to give myself some room. Let's continue up here. This leaves us with, over here, -2 in the exponent of the e. It's going to drop it down, giving us -1 over e squared, so with a 2. Minus 0, I won't write that. Here we get -1/4 e to the -2. Again, we're going to drop it, 4e squared, and then -1. Okay. Here we could combine these two by multiplying the top and the bottom by 2 to get a common denominator. So this is 4, this is 2. And we could combine now. -2 minus 1 is -3 over 4e squared minus 1. And this is the final answer. Okay. So a bit more work because we have to apply FDC part 2 at the end, but it's essentially the same game plan as we saw for indefinite integrals. Okay, so let's look at the next example. So here, example 2, evaluate the integral from 1 to 2 of ln of x divided by x squared dx. So pause the video, give this a shot, see if you're able to solve it on your own. One thing you have to be careful for is this function continuous, and is it continuous on the bounds that were defined on, in this case from 1 to 2? Well, the answer is yes. Be careful here, x cannot be 0, you'd be dividing by 0, that's an issue. The function wouldn't be continuous, but 0 is not in our bounds of integration, so we're okay. You could go ahead and use integration by parts. Again, same issue, there's a division here. Integration by parts, typically there's a multiplication of two different types of functions. Well, we could just rewrite this as we did in the previous example, ln of x times x to the -2. We're going to bring the x squared up and switch the sign of the exponent. And now we're dealing with a multiplication, and you could apply integration by parts. Using LIATE, we're going to let u equal ln of x. So the second you have a logarithm, an ln, that's right away our u. Okay. The issue with u being ln, if you miss that and you let your dv equal ln of x, and then you have to integrate ln, it becomes very difficult. So right away, it's easier to derive ln of x. We know the derivative of ln of x. We don't know the integral of ln of x. So do not let your dv equal ln. Okay. So using LIATE, this is our u. Whatever's left over is our dv. Now that we have our u, we take our derivative. So the derivative of ln of x is 1 over x dx. And the integral of x to the -2. Again, you could do this on the side, but this is essentially just power rule. We add 1 to the exponent and divide by that value. And this is it. So now from up here, this is side work. Let's go ahead and continue down here. So following our pattern from top left times bottom right, this is how we remember the formula. U times V minus the integral of V du. So this times this, ln of x times x to the negative 1. So it's negative, and we could think of it as over x. If you drop the x, it becomes positive. So we get negative ln of x over x. And we're evaluating it from 1 to 2. Minus the integral, again from 1 to 2. We do not change the bounds of integration because we're not applying a u substitution. This is integration by parts. The bounds of integration stay the same. And now it's v times du. So x to the negative 1. I'll rewrite it as 1 over x. And since it's negative, I'm just going to switch the sign to a positive. This times our du, which is in this case 1 over x dx. And this is easy to integrate. So we have we're simply applying FTC part 2. And this over here is basically just 1 over x squared. 1 over x times 1 over x is 1 over x squared, which is the same as just bringing it up, which is x to the negative 2. And now we just use power rule. So we add 1 to the exponent and divide by that value from negative 1 to 2. From 1 to 2. And now we apply FTC part 2. So we evaluate at the upper bound and the lower bound. So this gives us, there's a negative in the front, open bracket, ln of 2 divided by 2, minus ln of 1 divided by 1. Okay, separated by a plus, I'm just going to continue down here. Evaluate at the upper bound. This we could rewrite it as, well, the negative we could pull it out, just to make it simpler. Change this to a negative, and the x to negative 1 we could write it as 1 over x. I think it's just easier to do it this way. So we get 1 over 2, we substitute the 2 minus the 1 over 1. Okay. ln of 1, this we have to know is equal to 0. And we're left with negative ln of 2 over 2 minus a half plus 1. Right? Because the negative here distributes to this negative and you get a plus. Okay, negative a half plus 1 is just positive a half, so this leaves us with a half minus ln of 2 over 2. And we're done. This is the answer. You could factor out a half if you want, leaving 1 minus ln of 2, but this is fine. Okay, and this is the answer. So let's go ahead and keep practicing. So in the following example, we have to evaluate the integral from the square root of pi over 2 to the square root of pi of x cubed times cos of x squared dx. So give this a shot, pause the video, see if you're able to solve it. So the trick with this question is well, we have a multiplication, so this is an integration by parts problem, but we're dealing with this x cubed and the x squared inside the bracket. So how do we get rid of it? My first instinct here is to apply u substitution and let u equal x squared. Okay, so let's go ahead and do that. So letting u equal x squared. So here we're applying a u substitution first, and then we're going to apply integration by parts. The derivative of u with respect to x is 2x, and solving for dx, we get du over 2x equals dx. Okay. Since it's a definite integral, we have to change the bounds of integration. So plugging in the upper bound here, the square root of x squared. So sorry, the square root of pi squared is just pi. Since you're just squaring the terms, the square and the square root cancel each other, leaving us with just pi. And same for here, on the lower bound, we get just pi over 2. Okay, so make sure you change your bounds. X cubed, there's nothing we could do, we have to leave it. Then we're left with cos of u, because u is equal to x squared. And dx, we solved for it here, we're left with d over 2x. Okay. With a bit of simplification, we have x cubed divided by x, which is just x squared. And the 1/2, let's just set them in the front. Okay. But we still have this x squared, which is an issue. Remember, u substitution has to be expressed solely in terms of u. We have an x, we don't want that, but look back to our substitution, u is equal to x squared. So instead of writing x squared, we could rewrite this as u, and our u substitution is done. Now it's written solely in terms of u. So now we're happy, we could go ahead and apply integration by parts because we have an algebraic function multiplied by a trig function. So using LIATE, what do we call our u? for integration by parts? Well, we're using a and we have t. So t is the cos of x or cos of u, and a is the u or x, whichever way you want to think of it. So we're gonna let u equal u. So obviously I can't use u equals u. That's confusing for your readers, so we're gonna call it something else. So call it like u1, or I'm gonna call it u bar. Just use a different notation. So u bar equals u, and we'll keep it with v. So dv equals whatever's left over. In this case, cos of u du. Okay. So if we take the derivative of u bar, it gives us the derivative of u, which is just du. And if we're gonna integrate dv to get v, what's the integral of cos? Well, the derivative of sine is cos, so the integral of cos is sine. Okay. And now we use our rule. The integral of u dv is equal to, so now this is essentially side work. This is stuff we do on the side. Now we jump down here from here. The 1/2 is still sitting in the front, and what are we left with on the inside? We're left with u times v, or in this case u bar times v, which is u sine u. And we're evaluating this from pi over 2 to pi, minus the integral of v du, du bar in this case, which gives us sine of u du. And we're evaluating it again from pi over 2 to pi, with the 1/2 sitting in the front. So let me erase and give myself some room. And let's go ahead and solve this. So let's sit the 1/2 in the front. We're gonna jump back up here. We have 1/2. Here we're gonna apply FTC part 2 on this piece. So I'm gonna substitute the pi, giving us pi times sine of pi minus pi over 2 times sine of pi over 2. Okay. So this is the first piece inside our big square brackets, minus, I'm just going to jump down here. I apologize for this, I just don't have space. Now we're going to integrate sine of u. So again, the derivative of sine is cos, the integral of sine is negative cos. So the two negatives, the negative from the minus over here, the subtraction, and the fact that we get negative cos turns it into a positive, and we're left with cos of u, and we're evaluating this from pi over 2 to pi. Okay. And close big square brackets. Let's keep going. So we still have the 1/2 on the outside. First big square bracket. This piece here we have sine of pi. Sine of pi, remember your unit circle is simply just 0. So this piece here is cancelled. And then we have pi over 2 times sine of pi over 2. Sine of pi over 2 is 1. So we get just negative pi over 2. Okay. Plus, and here we have cos of pi, the upper bound minus the lower bound, minus cos of pi over 2. Okay. Cos of pi is negative 1 from our unit circle. And cos of pi over 2 is 0. So this piece is gone. So we're left with 1/2, which we'll distribute in, minus pi over 4, and then the 1/2 times the negative 1 minus 1/2. And this is the final answer. We're done. Okay. Let's move on to the next example. So example 4 here, we have to evaluate the integral from 0 to 1 of arc tan of x dx. Again, pause the video, give this a shot, see if you're able to solve it. Using LIATE, we have log, inverse trig, algebra, trig, exponentials, and all we have here is, well, it seems that we're just dealing with an inverse trig. But we could think of this as arctan of x times 1 dx, where the 1 is essentially your algebraic function. You can think of it as x to the 0. So this is our 1. So in this case here, I'm going to let my u equal arctan of x. So letting u equal arctan, we have to go find our du, and whatever's left over, 1 dx, oh sorry, that's our dv, and we have to go get our v. So here we're gonna derive, here we're gonna integrate. The derivative of arctan, we have to keep this in mind, is 1 over 1 plus x squared dx. Okay, and the integral of 1 dx is simply just x. Okay, so we're integrating with respect to x, so we're left with just x. And now we could apply, this is side work, we could apply our integration by parts. So we're going to multiply u times v, in this case x times arctan of x. And we're evaluating it from 0 to 1 because it's a definite integral, minus the integral from 0 to 1 of v du, in this case x times 1 over 1 plus x squared dx. Okay, so this piece here we could do, this is fine, this is an issue. Well, we could think of it as x over 1 plus x squared. So I don't know if this helps, but essentially what we have here is a u substitution, because notice that the denominator has 1 plus x squared, and on the numerator we have the derivative of 1 plus x squared sitting there. So this is a u sub. This piece I'm just going to leave it out for now. Let's focus just on this piece for now. And we use the letter u, so I'm going to use some other letter. Let's use u bar. So we'll call u bar 1 plus x squared. Now I'm applying a u substitution, so be careful. We have to change the bounds of integration. So the derivative is 2x dx. So this piece here, from 0 to 1, this is work on the side, dx. This thing here transforms into the integral. If I plug in the upper bound, we put 1 squared plus 1, which is 2. And the lower bound, we're plugging in 0, replacing x with 0. We get 1 plus 0 squared, which is 1. Okay. The x on top, we have to leave it. And on the bottom, we're replacing the 1 plus x squared with our u bar. Next, we just have to substitute the dx. And solving for dx here, we get du bar over 2x. So this is du bar over 2x, which is great because our x's cancel. So our u substitution works. Might as well go ahead and solve for the value. Again, this is all side work. It's not part of this. It's not a continuation. This is just side work. I'm focusing on just this integral here. And this leaves us with 1/2 integral from 1 to 2 of 1 over u bar du bar. The integral of 1 over u bar is just ln of x. So we have a half ln of, in this case, u bar from 1 to 2. We're going to take this, apply FTC part 2, giving us ln of 2 minus ln of 1, and we know ln of 1 is 0. So this is just simply ln of 2 over 2. Okay. So the upper bound minus the lower bound ln of 1 is 0, that cancels out, so we're just left with the upper bound and the 1/2 in between. So this piece here, we're just simply subtracting the ln of 2 over 2. Okay, so let's erase this. Again, this was done on the side. So this is equal to x arctan of x. We're going to substitute the 1. So 1 times arctan of 1 minus 0. Because 0 times arctan of 0 is just 0. And then minus this piece here, we just solved for it. It gave us ln of 2 over 2. Okay. Arctan of 1, this is a bit tricky. But how can we write this? This gives us pi over 4 from our unit circle minus ln of 2 over 2. Okay. You're basically asking yourself what values of what angle causes arctan. You could think of it tan as sine over cos, sine theta over cos theta, and you want to know which angles, when you divide them, would give us 1. Well, this occurs when on our unit circle, if we look at it quickly, when cos and pi are both root 2 over 2. And at what angle does this occur at? Well, this occurs at pi over 4. Okay. So arctan of 1 is pi over 4 because when you divide sine over cos, sine of some angle divided by cos of some angle, specifically the angle pi over 4. Root 2 over 2 divided by root 2 over 2 gives us r1. So this arctan of 1 is simply pi over 4. Okay, and this is our final answer. So in the following example over here, we have to prove a statement. So if f of 0 equals g of 0, which is equal to 0, and f double prime and g double prime are continuous functions, then we want to show that the integral from 0 to a of f of x times g double prime of x dx is equal to f of a times g prime of a minus f prime of a times g of a plus the integral from 0 to a of f double prime of x times g of x dx. So let's go ahead and give this a shot. Pause the video, see if you're able to do this on your own. I think you could get it in 2 steps. Okay, so the first thing to notice is the fact that we have a multiplication of 2 functions. We have f of x, some function f of x, and some function g double prime of x. And we want to transform this. We want f of x to turn into f double prime of x, and we want g double prime of x to turn into g of x. So f of x, what I'm thinking of doing is taking the derivative of that function, because we want the double derivative. And since we have the double derivative here and we're trying to go back to the original, I'm thinking of taking the integral of this function twice. So that's my game plan. Let's go ahead and give it a shot. So since we have a multiplication, integration by parts is what I'm leaning towards. So let's go ahead and do that. We have u equals the function f of x. dv equals what's left over, namely g double prime of x dx. We take the derivative of f with respect to x, giving us f prime of x dx, and the integral of the integral of dv giving us v, which is going to give us g prime of x. Okay, so now we do u times v minus the integral of v du. We apply our integration by parts. And this thing over here, so this is the question mark. We're trying to show this is equal to this. But if I start with the left-hand side, the integral from 0 to a of f of x times g double prime of x is equal to u times v. U times v, in this case f of x times g prime of x, evaluated from 0 to a, minus the integral of v du. In this case here, we're integrating from 0 to a of f prime of x times g prime of x dx. The order in which you multiply doesn't matter, so I put f prime first, just to stay consistent with our notation here. Okay. So now here we could apply FTC part 2. So we could evaluate it at the upper bound a and then subtract it by the lower bound. But recall, let's write it out. We have f of a times g prime of a minus f of 0 times g prime of 0. Oops, not x, 0. So this is FTC part 2. We did the upper bound subtracted by the lower bound, giving us this. Well, f of 0, we stated that f of 0 is equal to 0. So this whole piece here is gone. Right? F of 0, which is 0 multiplied by anything, is 0. So we're just simply left with f of a times g prime of a. So I'm going to remove this piece. Okay. Now we have to deal with this piece. So we have a subtraction here in the front. But how do we deal with this piece? Well, this is a second integration by parts. We're going to let you, remember, we have f prime. We went from f, we transformed it to f prime, which is great because now we want f double prime. So let's use another integration by parts. So having done u and v, let's call it u1. I'll call u1 f prime of x. I'll call this dv1 just to change the notation from what we have here. dv1 is g prime of x dx, whatever's left over. And we take the derivative of u1, giving us f double prime of x dx. And here we're going to integrate g prime of x, giving us v1 is equal to g of x. And using our integration by parts, top left times bottom right, minus the integral of bottom right times bottom left, we get u1 times v1, so f prime times g prime. Wait, f prime times, sorry, not g prime, just g, evaluated from 0 to a. And let me just erase here, minus the integral of v1 du1. Minus the integral, I should put all this in brackets because we have a minus that's subtracting everything. Minus the integral of, from 0 to a, of v1 times du1. which is f double prime of x times g of x dx. Okay. So this negative and this negative, this, if we distribute the negative, turns this positive. So that's positive now. I'm going to remove the bracket. Okay. Which gives us the first term. This is what we have here. Okay. And here, if we apply FTC part 2, we get f of a times g prime of a minus f prime of a times g of a. Let me put this in brackets. Minus f prime of 0 times g of 0. And recall, g of 0 we said is equal to 0. So this thing is 0. So multiply 0 times anything, we get 0. So this piece is gone. So we're left with just this. F prime of a times g of a plus this piece over here. The integral from 0 to a. F double prime of x times g of x dx. And this completes the proof. Okay, that's exactly what we wanted to show. We started with the left-hand side, which I erased. Oh no, sorry, it's right here. We started with the left-hand side over here, and we showed that it's equal to this piece over here, which is the right-hand side of the equation. So we are done. So I hope this video helped. I hope you have better understanding of integration by parts, and keep practicing. I'll see you in the next video.